In this video, we will continue our discussion of line integrals by working another example. We have that line integral. The segment, this path is the segment. This is line, right? It's a straight line from -3, -1 to 2, 5. We are going to create our path here, but how we're going to do this is I need to figure out a path for x of t and a path for y of t, and then I'll put them in my r. This is a linear path. We are going from, like our x is going from -3 to 2. The change here, right, how much it changes, and we're not going to write change of x, is -3 up to 2. That's a +5. You could also subtract 2 minus -3, right? Wherever you go, minus initial. So how we're going to write this is going to be 5t, because that's the growth, and then I'm going to put a -3. Notice I just did y equals mx plus b. But instead of doing y and x, we are doing x and t. So x equals the slope, how far it goes, is 5t, and then b is just your starting. Well, it started at -3. So I'm going to put a -3. Okay, that's x. We can also do y like that. Okay, y goes from -1 to 5. This change is +6. So if I do y equals mt plus b, I get y equals the change was 6, and then the starting was -1. So we can come up with segments as long as it's a straight line like that every time, and this is going to give me an r. Okay, I'm going to move this because I know I'm going to use quite a bit of room. Let's move this over here, and then I'm going to shrink this up and just put it up there. All right. So that's how you come up with your segments. Let's write our r of t now. We have each part. The x part is 5t minus 3. And then the second part is 6t minus 1. Anytime you set it up this way, t is going to be 0 to not 0, but 0 to 1. Every single time. So I'm going to write that here. If you define it like we just did. This helps with r prime now. We can find that. R prime is 5, 6. Which means the magnitude of r prime is the square root of 25 plus 36. Which is the square root of 61. Right, not clean, I'm just going to leave it alone. All right, now we can actually jump to our integral. We have our definition. I think I still have this. Yeah, okay. I'm going to put it in terms. So we have the integral of c minus 3xy ds is equal to t equals 0 to 1. I redefine my x's and y's with what they are. 5t minus 3 times 6t minus 1. Then I times the root 61 dt. All right, let's bring out our -361 and then go ahead and multiply by using FOIL, or I use a boxing method in my head. 3t squared, I got -18, -5 makes -23t, and then I got a +3. Check with my notes. Yep, everything's looking good. All right, now we can integrate that. That's just straight integration with the power rule. So we got 30 over 3, which is going to be 10t cubed. I always do my derivative backwards, so 3 comes down, makes 30t squared. Cool. And then I got 23 over 2t squared plus 3t. And we're going to plug in 0 to 1. I don't really need to write t's. I don't have multiple variables. So I got 3 root 61. Notice that all the zeros are going to zero out. And I got 10 minus 23 over 2 plus 3. This, if you were to work it out, I'm not going to do it on here for the sake of time, we get -9 square roots of 61 over 2. All right, so just some algebra. The segment is the new thing there. We just define our segment using mx plus b. I think in your book, I think Professor Leonard, a few other professors online that I like to go see how they approach things, don't follow the mx plus b. They have a formula. I think less formulas is better. I think relying more on something you already know, mx plus b, helps a whole lot.